Hey guys, welcome. Yeah. So I hope you've all been well and coping, just trusting Jesus, you'll be fine. And yeah, so I'm back here with a second example on Lagrange multipliers. If you don't recall, I provided you a first example where we maximized the surface area of a box given a fixed volume. And so there I showed you how to use the method of Lagrange multipliers on a function f of x comma y. Here we're going to look at a harder example where we're given f of x comma y comma z, and that is x squared times y squared times z, subject to this constraint. This constraint is also unusual in the method of Lagrange multipliers, as usually, as usually it's equal to, not lesser or equal, right? But here we have lesser or equal. So how do we deal with an example like this is the question. Well, that's what this video is about, so don't fret. All right, now, first, we must consider when we have strictly less than and then when we have equal to. When we have equal to, we're going to use the method of Lagrange multipliers. But when it's strictly less, it turns out that we just have to find critical numbers. What we're doing here, by the way, if it's not clear, is akin to finding absolute or global maxima and minima in Calc 1. Remember, what you did there is you considered endpoints as well as critical numbers. And so when we have strictly less than, that is inside the region, that is when we have this, then we could just simply find critical numbers, right? And critical numbers, since we're working with a multivariable function, amount to setting partials equal to 0. Specifically, we set the partial with respect to x and then y and then z, each equal to 0, and then we find some critical numbers, right? Now, since our function f of x comma y comma z is x squared times y squared times z, we see that the partial with respect to x is going to look like this, partial with respect to y is going to look like this, and partial with respect to z is going to look like this. Now, I have several videos on partial derivatives, so I'm not going to talk through the details of this. But let's consider the first partial equation, this, right? And so that's when the partial with respect to x is equal to 0. So we'd have this. Now, look at this. So if either x or y or z is equal to 0, the whole thing is equal to 0. So what we're saying is one critical number would look like 0, comma, any a, comma, any b, where a and b are real numbers. So this is one possible critical number. Well, it's actually like infinitely many since we're choosing a and b to be any real numbers. But yeah, this is what a critical number would look like. But if we also look at the other partials altogether, we see that the other partials being equal to 0. Altogether, we see that we have other varieties of critical numbers. In other words, if y is 0, this whole thing is 0, and so all three partials are equal to 0, right? And also, if z is equal to 0, the partials are 0. So these are the three critical numbers that we'd get out of the partials being equal to 0. Now, if we evaluate the function f at any one of these critical numbers, notice that what we're going to get is 0, right? Because, well, if we plug this in, we'd have 0 squared, a squared, and then b squared. Well, that's 0. If we plug this critical number in, we're going to get a squared times 0 squared times b. Well, that's also 0. You get it. So for all three critical numbers, the function's value is equal to 0. That can't be the minimum or the maximum value. Well, let's find out by considering now what happens when we have equal to in this part, right? So we're not in the region, we're on the region, right? So on the region, when we have equal to, we use Lagrange multipliers. So this is the moment you've been waiting for, right? Okay, all right. Now, for the method of Lagrange multipliers, as I said in that first example, right, there are two approaches. And this is probably what you're used to in your class, which is you take this, which is the gradient of f equal to lambda times the gradient of g, right? You take this equation, and by the way, you should know that this equation is really three different equations. You take it together with the constraint function, and so that's the first approach. And again, as I said, this is really three equations, because, well, one equation is the partial with respect to x is equal to lambda times the partial with respect to g. Another is the partial with respect to y of f is equal to lambda times the partial with respect to y of g. Okay, I said that first part a little too fast, but I made up for it by clearly spelling it out when we got to the partial with respect to y of f is equal to lambda times the partial with respect to y of g, right? It's really three equations. Augmented function, and the two approaches are consistent. They're the same. They end up in the same place. In fact, in this video, I'm going to convince you, like I did in that first example, I'm going to convince you that the two approaches are the same. But crucially, in both approaches, the function g is basically the constraint function all on one side. In other words, this number is subtracted to the left, and so it would look like this then once we do that. And so that's g. G is with this constant on the other side, right? So g is when the constraint is equal to 0. It's the left side of equal to 0, if that's not clear. Okay, I said it in a number of ways. But again, this is the g you use whether you use the L approach or the typical approach, which is going off of this and then the constraint. Now, the L approach, again, L is called the augmented function. This is all I did in college. So all we did is just use the augmented function when we did Lagrange multipliers in college. As I said, the two are consistent. I'm going to convince you. But if we go with the augmented function approach, then the first thing you do as soon as you write down the L function, which is clearly f minus lambda times g, where again, g is as I've spelled out. But yeah, the L function is always constructed by doing f minus lambda times g. Yeah, and what we do once we construct this L function is we take four partials with respect to x, y, z, and then lambda, and set them all each equal to 0. Sorry, I'm laughing because like I'm talking really fast because I want to get this done. But like, yeah. Okay, so the partial with respect to x of the L function is going to look like this, right? The partial with respect to y of the L function is going to look like that. Again, I have many videos on partial derivatives where I discuss them from beginning, which is where they come from, to like thorough examples. So I'm not going to talk about partial derivatives in this video, but if you do it correctly, the partial with respect to x of this L function, which is this here, it's going to look like that. The partial with respect to y of the L function is going to look like this. The partial with respect to z of the L function is going to look like this. If it's not clear, L is a function of four variables, x, y, z, and lambda. So we can also talk about the partial with respect to lambda of L, and that is going to look like this. Now, here is a place where we talk about how the two approaches are consistent. Remember, the first approach was to take this, which is three equations together with the constraint, and the second approach, obviously, is to construct the L function and then to write down these four partials. And as I said, the two approaches are consistent, and here's where I explain how they're consistent. Well, see, if we take the partial with respect to lambda equaling 0 from the L function, what we're going to get is that this is equal to 0, right? Well, we can divide on both sides by -1, and then we could add 1 to both sides to get this. This here is equivalent to the constraint function. So in this second approach, that is, in the approach of using the augmented function, we see that the partial with respect to lambda is always going to get us back the constraint function. Otherwise, as I said, this here is really three equations, right? And the first approach, what we wrote over here in the box is at you about it. The first of them is going to look like this. But well, if you execute this, which is an execution, what this is going to say is this. But wait, this here is the same as equation 1 here. It's the same as what we get when we do the partial with respect to x of L and set it equal to 0. Yeah? Okay. And of course, you can see then, without too much leap in imagination, that the other two are going to be the same as doing the partial with respect to y and then z on this fella, right? So basically, the two approaches are identical. It's just the construction that makes them look a little different. Now, because the L function kind of has everything all in one place, like my channel, So what we're gonna do is just go with the L function, right? Now, the four partials that we have set to equal 0, well, if we move the lambda quantities to the other side, they're gonna turn into the following. In other words, add this to both sides of this equation, and then add this to both sides of this equation, and yada yada. If you do that, this is what you're gonna get. Well, equation 1 is gonna turn into this, equation 2 is gonna turn to this, 3, and then 4, right? Okay, so we probably need space, so let's get rid of that. Now, if we multiply these first three equations by x, y, and 2z respectively, remember what respectively meant. It meant, and still means, in order, right? So if we multiply them by x, y, and 2z in order, that's the first equation, the second equation, the third equation. Well, upon multiplying this first equation on both sides by x, we're going to first write this, and then that simplifies to this, right? And then the second equation, we're going to multiply both sides by y. And so first we write this, that's multiplying this on both sides by y. We write this, and then that simplifies into this, right? Remember, we're multiplying both sides by y. So in this part, we need to get y squared as I have, yeah? And the third equation, we're going to multiply on both sides by 2z, and the third equation being this here, right? And see, the respectively would have like taken care of that. I didn't need to narrate it, but I thought maybe some of you are like deficient in English or something. But anyway, you see the reason why we wanted to do this, which is multiply the first equation by y, the second equation by, the reason why we want to do this, which is multiply the first equation by x, the second equation by y, and the third equation by 2z, is because then the left side of each of the first three equations would become the same. This, and this. Now, once you get to your partials, your four partials, the way that you're going to finish the problem is going to look different from problem to problem. So that's just the nature of Lagrange multipliers. But in this specific problem, the easiest way out was to do what we did here, which is recognize that multiplying the first equation by x, the second equation by y, and the third equation by 2z would create this convenience. So basically, you need to keep your eyes peeled to like whatever it is that you need to do to get the stuff done. But in this question, the problem done. In this question, what we had to do is this, right? And so we see then that since the left side of these first three equations is now the same, the right sides must equal each other. That is, this here must equal this here, which in turn must equal both of them equal to this, right? Okay, so that would have us write this equation. Cool. Because then we could divide on all three parts of this equation by 2 lambda. And you could like figure out why lambda is non-zero. But basically in the four partials that we had set equal to 0, if you solve for lambda and do all the substitutions and get an equation in lambda, you'll see that lambda cannot equal 0. And so then that means we could divide by lambda. Specifically, what we said is we're going to divide all parts of this by 2 lambda. When we do that, we're going to be able to write this much more succinct equation. Oh, how nice. Because now we're saying x squared is equal to 2y squared, and then in turn equal to 6z squared. Once here, we're on the home stretch. Once we've got this much more succinct equation, we're practically done. Why, you say? Because think about it. What's the only equation we haven't used? The equation where we set the partial with respect to lambda of L equal to 0. But wait, that's the same as a constraint function, right? So the only thing we have not used is the constraint equation, not function. Okay, but once here, we're on the home stretch, clearly, because we've got this really nice relationship between x, y, and z, right? And ask yourself, what's the only equation we haven't used? The only equation we haven't used is the one about the partial with respect to lambda of L equaling 0. That's the same as the constraint equation, remember. We'd said that. So if we recall the constraint equation, which is this, then using this nice relationship that we've come up with relating x, y, and z, but really x squared, y squared, and z squared, we can substitute in here and get this equation all to be about x, and therefore we can solve for x. Specifically, we can clearly see that 2y squared is simply equal to x squared. So in place of 2y squared here, we can write x squared. Also, if x squared is equal to 6z squared, then 3z squared is 1/2 x squared. So in place of this, we can write 1/2 x squared. So doing everything that I just said, we can write this in place of the constraint function. Oh, constraint equation. It's not a function. Constraint equation, right? Would turn into this, and then simplifying this, we'd get this. And this is easy enough to solve for x. First, we do that, and then next we do this, right? Okay. Also, since we already know that x squared is equal to 2y squared, and we know in turn that x squared is equal to 2 over 5, it means that 2y squared is equal to 2 over 5. That means y squared is equal to 1 over 5. That means that y is equal to plus or minus the square root of 1 over 5, right? Okay. So, finalement, 6z squared, right? 6z squared is equal to x squared. All right, but that's 2 over 5. Got it. But then dividing by 6 on both sides, we see that z squared is going to be 1 over 15, which means that z is equal to plus or minus root 1 over 15, right? Okay, cool. So we've solved for x, y, and z. And since we recall that f of x, y, z, f of x, comma, y, comma, z is this, right? All we have to do is substitute in these values and see which is biggest and which is smallest. What am I saying? I'm saying this. Let's make space, and we see that the minimum is this. Notice that although we get positive and negative y and x values, since they're the same value in absolute value, and moreover, because f is squaring x and y, we don't need to distinguish between the plus or minus in front of the square root of x or y values. But the z value, which is both positive and negative 1 over 15 inside the square root, right? You can clearly see, I need to spell that out. But because z comes as positive and negative, we see that the negative one is going to give us the minimum and the positive one is going to give us the maximum. Now, of course, we needed to consider the critical numbers also, but we did earlier. And what we found is that at all critical numbers, the function f returns the value 0. So that's not going to be the maximum or the minimum. This is the minimum and this is the maximum. Yes, I could have squared this and simplified the numbers, but I'm not much of an arithmetic person. And so since I did a lot of work to teach you here, I feel what I've done suffices. Okay, cool. Keep watching. Lots more to come. Take care.